Huh? So that's begin our class. Last week, not last week, Tuesday, we talked about a minus 3 dB line to define the bandwidth of your spectrum. Okay. But don't forget, you need to write the low frequency, lower corner frequency to higher corner frequency in order to identify the bandwidth. Okay. Don't do a subtraction because it's meaningless. Okay. And okay, so after, of course, after we know the minus 3 dB line, we can get a corner frequency. Okay, but how to get a final response? Okay, after we apply the filter to the original signal, then we need to calculate the ratio. Okay, so for the factor, amplification factor, even though sometimes it's attenuation, sometimes it's bandpass, bypass. Remember? We talk about this. Okay, this is the factor, right, or the ratio. If it's zero, if it's 0 dB, that means this is one. Okay, so this it means bypass. But if this is less than one, and the dB level, the dB value will be less than zero. Okay, so it's become attenuation. So this is represented by this one. Okay, over here, the ratio is always 1 or lower than 1. So that means in this range, in the frequency in the bandwidth, within the bandwidth, it's bypassed. Okay, and above or below the bandwidth is attenuation. So the ratio is less than 1. Okay. So if you transfer to dB, it will become 0 here, and all the value here will become minus. So it's very obvious to me. Yeah. But I know for some DSP engineer, they would like to see this in linear scale. So either one is okay. So how to do that? Of course, you need to calculate the ratio first at each frequency. So what's the frequency you are interested? You are interested in the fundamental frequency and also all the harmonics frequency in your Fourier series, right? So for example, that's for the two second harmonics, 2 omega 0, and the ratio is 0.25. So how to do that? You just multiply the factor, which is the 0.25, right, to the amplitude of the second harmonics, which is the A2. A2, A2, A2 here. This is the A2. Okay, so you multiply 0.25 to A2, then you get 0.25 A2. Then you can get the final amplitude. Then within this bandwidth, nothing can be changed. Okay, for example, this is A3 for the third harmonics, and this is also this is also A3 for the third harmonics, right? So it's all the same until it reach the frequency above the corner frequency. The corner frequency is not shown here. It's somewhere here, 0.707, right? So 0.707 is somewhere here. So above this higher corner frequency, the value begins to be attenuated. Okay, so for example, for this 10 harmonics, and the ratio is zero point 0.5. Ratio is zero point 0.5. So you times zero point 0.5 to the original value of the 10 harmonics, which is the A. What is that? It's not A1 and it's not A2. Somewhere in between. Okay. So anyway, it's zero point 0.5 times the original value of the A10. A10, right? Okay. And this is sine omega t, and omega is the 10 omega 0, 10 harmonics. So the signal can be original continuous signal can be represented as the Fourier series using this Fourier series uh, polynomial. Okay, it's a little bit hot. Next time I need to ask PA to turn on the AC. See? No power. Okay. I need to change the battery here. So any question? Okay, you need to know what's the bandpass, what's the attenuation, and what's the corner frequency in this spectrum. Okay. Okay. Next, we talk about the filter. Yeah. The filter we talk about here are very simple. Only four. The first one is low low pass filter, the low pass filter, and the second one is the inverse high pass filter. The third one is the notch filter. Here, notch filter, and notch filter is nothing but the inverse. Oh, no. We should say after high pass we have the band pass filter, band pass filter, because band pass is the combination of the high pass and the low pass. Okay, so you combine both low pass and high pass, you can get a band pass. You, if you inverse the band pass, it will become notch filter. It will become notch filter. Okay, so what's the band pass? Bless you. It's very funny when I learned English in Taiwan before going to abroad. I know what bless you, but after I go to US, and whenever I sniff like you, and everybody says bless you to me, I'm very surprised. I mean, something I learned in the classroom really being used in the daily life. It is very interesting. So what's the band pass? Okay, this is the low pass, right? But because this is not a log scale, so the attenuation is it's not obvious at all. Okay, but for example, if you using the log scale, this is the frequency, and using the log scale, and this curve will become like this. It's more sharp. Okay, it's more it drop more quickly. Okay, so this is the low pass. Okay, and if you add another kind of this is low pass, right? And when you inverse in terms of the frequency, then it will have high pass, something like this. Okay, then combine both, then you can have the band pass. What's the band pass? Band pass is just like the example we talk about. Now this is the band pass, but after you inverse, then it will become something like this, right? So, but this is not notch because this is too, the bandwidth is too wide. Okay, but if you move both corner frequency closer to close together, then finally it will become some frequency response like this. Okay, so after you inverse, then you need to decrease the bandwidth, and eventually you can get a very deep attenuation at a certain frequency. For example, 60 hertz, and this is what become notch filter. Okay, so notch filter not only the inverse of the bandpass, but also decrease the bandwidth. Okay, so you can the attenuation will become very deep. Okay? So we only talk about these four filters. Okay. And okay, so this is the most simple one, low pass filter. Okay. Uh, I talked to you before, in order to filter out the DC, and we can use a very simple one. Just use the capacitor, right? The one side of the capacitor connected to the input, and the other side is not grounded. It goes to the output, and this is the the simplest method to filter out the DC. Okay, but this is more formal. It's called low pass filter. So we can try to get the formula. Okay, in order to get the corner frequency. Okay, this is very important. So how to get that? We know two Kirchhoff law, right? One is KCL, one is KVL. Okay, and when you look at this, you want to get the output, okay, V out of the input, okay. So in order to get the V out of the V in, using two elements, of course, one is resistor and one is capacitor. What kind of the Kirchhoff law you need to use in order to get the voltage? KCL, KCL or KVL? Yeah. The answer is here, but I'm just asking you to speak out in English. What kind of Kirchhoff law? Kirchhoff current law or Kirchhoff voltage law? Which one? You want to try? Two options: Kirchhoff current law or Kirchhoff voltage law. Or you are talking. You need to use current division or the voltage division to get the V out. Which one? Yeah, yeah. That's very good, very good. Yeah, just doing some little conversation. Of course, this is apply Kirchhoff voltage law. Then you can get the voltage division out of this capacitor, right? But we are more familiar with the resistor than the capacitor. So how to get the fraction of the resistance out of the equivalent resistance? So we need to calculate the impedance, right? So in chapter 2, we learn impedance of the capacitor and also the inductor. Okay. If you remember, the impedance of the capacitor is 1 divided by j omega c. Of course, we can move the j from the denominator to the numerator. So it will become minus j divided by omega c. Okay. And the proportion is the impedance of the capacitance to the overall equivalent resistance. Now, they are connected in series, right? Connected in series. So we simply add R to 1 divided by j omega c. So this is the impedance of the capacitor. Then we can get the voltage division for the capacitor. Okay. Then we need to do some simplification. Simply times j omega c to the numerator and the denominator. So it will become 1 divided by j omega rc plus 1. Okay. Then we want to get uh, the magnitude. Okay. We need to get a magnitude. So for the denominator, then we can square root of 1 plus uh, omega rc squared. Okay, because we want to get the magnitude. Okay, then we define omega c is 1 divided by rc. So what's omega c? The omega c is the corner frequency of this filter, even though we don't know what kind of filter it is. Yeah, so this is the corner frequency of this filter. Then uh, because we know by definition the corner frequency, the voltage ratio is 1 divided by square root 2, right? Because for the power, it's one half. But for the voltage, it's 1 divided by square root of 2. Oh, the relation is this. Okay, the relation is this. Yep. So we put we replace 1 divided by RC as omega C. So this term will become omega divided by omega C. Okay. So if you pay attention to this formula, when the omega is very close to zero, that means DC, right? And this term will be out. Uh, this term will be out. Then uh, the whole term will become what, right? When the omega r, what's the omega r? This term is omega r, and that means omega is very close to a DC level. Okay, then when it become zero, then this term will become one. Okay, uh, note omega approach zero, AR approach one. What's AR? I think this is AR. It's not written here. The ratio, okay. The AR approach one. Okay. On the other hand, when the omega approach infinity, that means the high frequency. When the omega become very high, and this term will become infinity, right? Infinity. Then the whole term will become zero because the denominator will become infinity also. So this whole term is become zero, like this. When omega r approach infinity, AR approach zero. So that means at the low frequency it become one. It's one, okay. But for the high frequency, it's become zero. So it acts like a low pass filter. And the corner frequency is 1 divided by C. Okay, this is very important. Okay, so this is low pass filter, right? We just talked about. But if we add another one, but reverse the capacitor and the resistor, and it becomes this side becomes high pass filter. Okay, so we combine those two together, it will become band pass filter. And so when you are working on band pass filter, you need to get lower corner frequency using this one, right? Low, high pass. This is wrong because this is high pass filter, right? So high pass filter, so it becomes R2C2. No, R1C1. Sorry, R1C1. R1C1, and this will become R2C2. Yeah, because this is R2C2 for low pass filter, right? Correct? Okay. If you find something wrong in the PPT, please let me know. Of course, I'll give you extra point. Okay, so this is the band pass filter, and the corner frequency is one. This is in hertz, but when you move the 2 pi to the other side, and it will become omega. Okay, so omega C corner frequency of the low frequency is 1 divided by R2C2. Corner frequency of the high frequency is 1 divided by R1C1. Okay. Question? No. Okay. So we keep keep moving. Okay. And we only talk about the magnitude linearity so far. Okay. But in the very beginning, I talked about we want to discuss three topics. The one is magnitude linearity. The second one is phase linearity, and the third one is bandwidth. We talked about bandwidth already. It's related to the corner frequency. the corner frequency. Okay, high corner frequency and a low corner frequency. And so the last one is the phase. Okay, and in chapter 2 we talk about this. Okay, the AC signal, and this is the original signal without a phase shift. So this is simply sine omega t, right? But if you have another signal with phase difference, of course, it's related to the reference signal, which is the signal 1. Then you add some phase inside the signal 2. But depends on the sign of this phase. Then you know it's either phase lag. For example, by definition, signal lag minus sign means the signal lag. So this is the signal lag because this is minus 5, right? So what's the lagging? Lagging means it occurs behind or later than the signal 1. Okay, and this is the time axis, right? So when it occurs, this is 0 and this is 1, 2, 3, 4. Okay, so when it occurs later than the original signal, like this, it will move to the right. Okay, so lagging means it moves to the right side. Okay, with respect to the reference signal. Okay, the phase always can be calculated with the reference. Without a reference, there's no phase at all, right? For example, if you have only one signal, who cares about the phase? Who cares about the phase of the signal 1? If there's no signal 1, it means nothing to you, okay? For example, if you have only one speaker, and no matter what kind of phase it is, you still can listen to it. But if you have two speakers, then the phase begins to take effect. For example, if the phase difference is 180 degrees out of phase, and you will feel very when you hear it, it's very strange. It's like the sound is from out of nowhere. So you need to tune the phase of the both speaker without any phase difference, right? So the phase is always related to the other reference signal. So please pay attention to it. So, then you need to memorize the definition of the sign. Plus sign means leading the reference. That means it moves the signal 2 will move to the left with respect to the signal 1. Okay. Okay. So what's the phase? We talk about phase a lot. What's the phase? First of all, if you look at the unit of omega, the unit of omega is radian per second, right? Radian per second. And what's the radian? Radian is nothing but, for example, it, it use 2 pi, right? Yeah, it use 2 pi. 2 pi radian is correspond to 360 degrees, right? Degree. This is degree. This is radian. Okay. So on the other word, if you times because this is radian, the unit of omega is radian divided by s. So if you times the omega to by t, let me write omega times t, or 2 pi f times t, then it will become the unit will become radian. The unit will become radian because this is t, right? Means unit means second. So you times this to the omega, then the unit will become radian. Okay. So how about this? This unit is degree, right? So when you times this degree to t, then it will become degree. Correct? Because omega t is radian, but if you times the transverse omega, if you transfer omega to the degree, then it will become degree as well, right? So phi is equal to 360 divided by t, and this is f, right? Because divided by t, that we can inverse to the numerator. It will become f. So 360 f. When this is 2 pi and this is 360, right? And 360 f times the t. This is the t. Then it will become the phase. Okay. And this is on the other hand 2 pi f times t, because you move the t to the numerator and it will become f. So this is 2 pi f times t. Okay. And 2 pi f will become omega. So the unit of omega is radian. Unit of omega is radian divided by second. But if when you times the t, it will become radian. Okay. So this is very uh, interesting. The 2 pi, the most important thing is 2 pi correspond to the 360. Okay. So because of this, uh, when you said one system is has phase linearity, and that means the phase has a constant ratio with the frequency. So 5 is equal to kf. Okay. So let's take a look at this. If we change 1 divided by t as the f as the frequency, so the 300 times td will become here 360 td. 360 td will become k. Okay. Or for here 2 pi td. 2 pi td will become k. Okay. So if 360 td or 2 pi td is constant, k is constant, and that means you have the phase linearity. Okay. But what's the td? For small time displacement td, then what's the subscript for the td? Oh, here. For td is the phase. Okay, the time the time for the phase change. Okay, so when you measure the two signal, and you can measure their phase, right? The phase in the time domain, we call it TD here. TD here. So after uh, equal time displacement TD, okay, then if the phase is the same, so what's the same? 360 TD or 2 pi TD are is the same, and the constant, and that means you have the phase linearity. So let's take a look at the uh, this is time domain signal. This is time domain signal. Okay, and this is the original square wave, because we take the square wave as the example. But this is not close to the. This is close to the square wave, but something different, right? Something different. For example, at the corner, right? At the corner here, and for when this happens, the corner most of the time it means the high frequency. Okay, and at the center here it represents the low frequency, and that means there are some distortion, amplitude distortion of the square wave. Yeah, but this is not phase. I would like to talk about the phase first. Okay, uh, because uh, if the phase, if there are some phase difference between the high frequency and low frequency, and the curve will looks a little bit or a little bit tilted than the previous one. Okay, so for example, at this corner, it moves to the right side, moves to the right side, and by definition, when the signal lag the reference, it moves the right side, like this one, right? The signal two move to the right side with respect to the signal one. So when it moves to the right side, and that means uh, the high frequency component lagging. Okay, why the high frequency? Because it only occurs at a corner. Okay, when the signal only change at a corner, and that means something in high frequency has been changed. What kind of change? It changed in the phase. Okay, because it moved to the right side. Okay, so on the other hand, if the left side is moved to the corner is moved to the left side, and that means the high frequency component leading. Okay, because this is the time series. Okay, time domain signal, and the high frequency the high frequency because it's at the corner, right? But it moves to the left side. So that means the high frequency component leading. Okay, with respect to the reference signal. Okay. So this is the result of the phase nonlinearity of the high frequency, either lagging or the leading. Okay, but on the other hand, if we want to talk about the amplitude linearity, okay, for the signal, and we can use this example. Again, this is the corner. There are some difference at the corner, right? But at the center, the magnitude is the same. But at the corner, the amplitude decrease. Okay, so that means the high frequency distortion because the magnitude is different. Is different. But at the center is a low frequency. So if the center is attenuated, and that means the distortion at the low frequency. Okay. And then you said this is not a very, you can only take a look by your eyes. Is there a definition to talk about the so-called distortion of the signal? So we use an index called total harmonic distortion. Total harmonic distortion, and there's no specific rule of the PhD, but in the industry we always use 3% as the criteria. Okay, so because in the industry, in the factory, you need to have some kind of the index to define if this is the good stuff or the bad stuff. So they use a 3%. But by the hearing, 3% is too small for you to distinguish the bad one from the good one. Okay. So because I work on hearing aid for a long time, for the hearing aid or some hearing device, PhD 12% is the limit. So that means everybody can distinguish good one from the bad one. Whenever the PhD is reached, it exceeds 12%. Okay, but for the 3%, I think only a small amount of people can distinguish. So we call it golden ear, 金耳朵. Okay, so understand? Okay, this is how we define the linearity, either the magnitude linearity or the time demand uh, or the phase linearity of the signal. Okay. In the industry, we use 3% for this index, total harmonic distortion. Okay. So for this is a square wave, right? But in the industry, we use a sine wave. The reference is a sine wave, and this example in the textbook is square wave. Okay, so let me